How's everybody doing?
Good.
So did you understand my answer about the graphing?
Yeah.
Okay.
It took me a while, but I figured it out.
Okay. Okay, we'll go ahead and get started. First thing, I just wanted to remind everyone that on Wednesday, we'll be having a quiz, and that quiz will just be on chapter 3. Okay, so we're going to be talking about chapter 4 today. We're going to be talking about chapter 4 today, but the quiz on Wednesday will just cover chapter 3. So let's go ahead and get started on that, chapter 4 stuff. So in chapter 4, we're going to talk about aqueous solutions and reactions in aqueous solutions. And when we say aqueous solutions, what we're talking about is things that are happening in water as the solvent. When we talk about a solution, what we're talking about is a homogeneous mixture of 2 or more substances. And when you have that mixture, the molecule that's there in the greatest abundance is called the solvent. So for aqueous solutions, that would be water. And then the other substances that are in there, the other molecules that are in there, that are in at a much less concentration, those are called solutes. So solute is the lesser concentration, and solvent is the greater concentration. And when you talk about solutions, you usually don't give a concentration value for the solvent. You're more concerned about the concentration value of the solutes. And once again, when water is the solvent, we say that's an aqueous solution. So when you talk about forming an aqueous solution, we said it's homogeneous, right? So that means there's no precipitants in there and things like that. So how do you solubilize? How do you get those analytes into solution? Well, there's a couple ways that can happen. If you have ionic compounds, then those compounds dissociate. So that's a case of where you have a positively charged cation, negatively charged anion, and they dissociate, so they're floating freely in the solution. They're not bound together anymore by any type of chemical bond. So you have, for instance, sodium chloride is a real common one. So you have sodium ions, which are positively charged floating around. You'd have chloride ions, which are negatively charged floating around. And then you have the water molecules, which kind of go around those ions, and we call that solvation. So whenever things go into solution, whether it's ionic, or we'll talk in a moment about molecular, solvation always occurs. So with molecular compounds, these are ones that don't dissociate into cations and anions. We have molecular compounds, they stay intact, so they don't dissociate. They do interact with the water, however, and the water solubilizes them and gets them into solution. So down at the bottom, we have some visual examples of that where you have the salt crystal, sodium chloride crystal. The ions dissociate, the sodium and the chloride ions. The water solvates around that. And the other one example, I think, is a sugar molecule. I can't really see from here. It's methanol. Okay, methanol, where the water solvates around the methanol, and then methanol goes into solution. When compounds go into solution in water, we tend to think of them as being a strong electrolyte, a weak electrolyte, or a non-electrolyte. So if you ever see like Gatorade commercials or Powerade commercials and those types of sports drink commercials, they're always talking about electrolytes. And this is what they're talking about, is a strong electrolyte is something that dissociates completely when dissolved in water. A weak electrolyte only dissociates a little bit, and we'll have some examples of that in a little while. And then a non-electrolyte does not dissociate at all. So pure water in the first photo, pure water does not conduct electricity, so it doesn't have any electrolytes in it. So in other words, there's no ions floating around in pure water. There's just the water molecules. And it's the ions that allow you to conduct the electricity. It's actually really, really difficult to make pure water because there's always some kind of residual ion in there. So it's really hard to get water without any ions. The second example is a sucrose solution. So sucrose is a sugar. It dissolves into water. We know that. It's easy to dissolve sugar into water, but it doesn't dissociate into ions. It stays intact as the molecule. So it doesn't have any charge. Because it doesn't have any charge, then it's a non-electrolyte. And so it doesn't conduct any electricity. And then the other example they have is sodium chloride. So sodium chloride is salt, basically. And that is a strong electrolyte because the sodium and chloride completely dissociate. So you have a bunch of sodium ions, which are positively charged, and a bunch of chloride ions, which are negatively charged. So you've got a lot of plus and minuses in there, and that makes those ions are able to conduct electricity. So when they're talking about in those sports drinks about they have a lot of electrolytes, they're talking about having some type of salt in there. And the reason why you're concerned about that is to have just different processes in your body occur properly, you need to have movement of electrical charge. And so that's why you don't want to deplete your electrolytes. But it all gets down to this, what we're seeing here in these three pictures of you need to have strong electrolytes present in order to conduct electricity. And whether that's electricity like here where they're powering a light bulb or the electrical type things that go on in your body, either way, it's the same idea. So let's talk a little bit about the strong versus weak electrolytes and introduce a term that we really haven't had yet called equilibrium. So a strong electrolyte, as I said, totally dissociates in water. And so for here, hydrochloric acid, HCl, we would write the equation like this. We have HCl going one way, the hydrogen ions and chloride ions. So we have complete dissociation of that HCl molecule. And this is how we've been writing our equation so far with the arrow, just the one arrow, telling us that that reaction goes the whole way there. In this case, it's a dissociation reaction. The next one, we have acetic acid, CH3COOH. And this is a weak electrolyte. And what weak electrolyte means is that when you put it in water, it dissociates a little bit, but not the whole way. So we see this reaction written where we have acetic acid on the left dissociating to hydrogen ions and acetate ions. But we notice there that the arrow isn't just one way. We have arrow going to the hydrogen ion, acetate ion side, but there's an arrow going back to the acetic acid side. What that tells us is that if we took some acetic acid and put it into water and we analyzed what was in there, we would find acetic acid molecules, we'd find hydrogen ions, and we'd find acetate ions. We'd find them all. Versus HCl, if we put that in water and then analyze what was in there, we just find the protons, the H plus ions, and the chloride ions. We wouldn't find any HCl together anymore because that's totally dissociated. So in this second one, with the acetic acid, where we have that arrow going both ways, that's the equilibrium. And so compounds like acetic acid and these types of acids have something called an acid dissociation constant. We don't need to know that for right now, but I just tell you this, we'll get to this a little later in the semester. But that acid dissociation constant tells us under equilibrium conditions what the concentrations of those three components would be. And so there's ways to figure that out, and we're not going to go into that right now, but that equilibrium is just telling us that we don't go all the way to the proton and the acetate ion. We go partial of the way, and that's what equilibrium is. Equilibrium reaches a state that for that molecule, how much does it like to dissociate? And there's things you can do to drive these types of reactions one way or the other, and kind of do what they call shift the equilibrium. So does everyone get the difference between a strong electrolyte and a weak electrolyte? And does everyone understand what I mean by this chemical equilibrium thing, where we're not driving the reaction all the way, but it's kind of staying with all three components at different concentrations? Okay. So let's talk about some solubility of ionic compounds. So normally you think of ionic compounds as dissociating and being soluble in water. Well, that's not always the case. There are some ionic compounds that even though they're ionic, they're insoluble. And so we have some solubility rules which help us understand which combination of ions will dissolve and which ones will not. And so this is another one of these tables that you're going to have to spend a little bit of time memorizing to understand some of the solubility things with regards to these compounds. So if we look at ionic compounds that are pretty much all the time soluble, we have some anions here listed. So we have nitrate, the NO3 minus, we have acetate, CH3COO minus, we have chloride, bromide, iodide, and then sulfate. The nitrate and the acetate are always going to be soluble. So if you have whatever the cation is on that, it's going to dissociate and be soluble. Chloride has some exceptions. Silver chloride is a precipitant, mercury chloride, lead chloride, same with bromide, iodide, and sulfate. Of all those on there, the silver chloride one is a pretty famous precipitant in the world of chemistry. That's commonly used to do titrations to determine how much chloride is in something, is using that silver chloride precipitation titration. The idea here is to give you some examples of soluble ionic compounds. And for the most part, these will be soluble. There are some exceptions. And like I said, that silver chloride one is a biggie, and that's used all the time. So here's some examples of ionic compounds that are typically insoluble. So remember, soluble means it goes into solution. Insoluble means it will be a clump of something sitting at the bottom of the beaker. So sulfide, carbonate, phosphate, hydroxide, a lot of those form insoluble compounds, but there are some exceptions of things that are soluble. One that should jump out at you is ammonia, so NH4 plus. If it's an ammonia salt, it's usually soluble, irregardless of what the back end is, what the anion is. The other thing you'll see is the alkali metal cations. If one of those is involved, it's usually soluble. Does anyone remember which ones are the alkali metals? Can someone give me an example of one?
The first column?
Yeah, so that'd be like lithium, potassium, sodium, things like that. And the way I always kind of remember that is, if it's potassium and sodium, and you think about from a dietary perspective, people talk about potassium and sodium a lot, right? Well, that's because it's real soluble when those are involved usually. Because you think about it, if it was in your body and precipitating out, you'd have a problem. So that's how I kind of remember the alkali ones, is that sodium, potassium. We talk about that a lot with regards to food and nutrition and things like that. And so if it's in our body, it's probably not precipitating out. Ammonia is the other one. Just remember that if there's an NH4 plus on the front end of it, it's probably going to be soluble. So let's talk a little bit more about electrolytes and non-electrolytes. So if it's an ionic compound, it's usually a strong electrolyte. This is assuming that it's soluble, okay? So we have our solubility rules. It's got to satisfy that first and be soluble. But if it's ionic and it's soluble, it's almost always going to be a strong electrolyte. And that just means because those ionic compounds fully dissociate. That's the simple definition of a strong electrolyte, something that fully dissociates into its cation and anion parts. For molecules, it kind of depends. So strong acids and strong bases, those will dissociate the whole way. So like that HCl example we had, HCl is a strong acid. Sodium hydroxide would be an example of a strong base. Those dissociate the whole way, and because they dissociate into their cations and anions, those would be strong electrolytes. Most organic compounds fall under this weak acid, weak base category if they're going to dissociate at all. And that goes back to that equilibrium that we talked about with the acetic acid. Is that those organic acid type compounds or organic base type compounds usually have some type of equilibrium that they maintain, and some are stronger than others. If I say one acid is stronger than the other, what do I mean? Does anyone know what I mean by that?
The bonds are stronger?
Yeah, well, but I'm thinking a little more simple term. I'm just thinking that if I'm saying it's a stronger acid, I'm saying it's going to dissociate more, okay? So in other words, if it's an acid, it's going to give up more of those protons from the parent molecule. It's going to shift that way. And same with the base. If it's a strong base, the equilibrium is going to shift more towards that hydroxide ion being floating around. It's not total. It's not like a strong acid or base where it goes the whole way. But if I say something is a stronger acid or base than another one, and it falls into this weak acid base category. It just means it donates more of those protons for OH groups. The other thing with organic compounds in general is that a lot of them don't have any acid or base functional groups. And so they don't donate a proton or a hydroxide or something like that. And so in those cases, and this is the sugar example we had earlier, in those cases, you're not going to get any dissociation. So those are not electrolytes at all. Because remember, once again, electrolyte, when you put it into water, has to form ions. If it doesn't form ions, if all it does is dissolve, then it's not an electrolyte, it's a non-electrolyte. So it's that dissociation into ions that you have to be an electrolyte. So if we take two salts that are soluble and mix them together, and suddenly we see stuff precipitating out, that's called a precipitation reaction. So the key is you had two salts on their own. If you put them in the water, beaker of water by themselves, and they go into solution, everything's soluble. But now if I take those two beakers and mix the solutions together, then suddenly that combination forms some insoluble compounds. And here we have an example of that with potassium iodide, lead nitrate, and then we see that lead iodide is a precipitant. And so this would go back, this would take us back a few slides ago, where we talked about our rules and guidelines for soluble ionic compounds. So we see here that iodide, I minus, is usually soluble, but one of our exceptions was lead. So that's how we would know or be able to predict that we would get a precipitation reaction here. So you can use those rules just to predict when you put something in a solution, should it go into solution, should it dissolve? And you also can use those rules to predict if then I start mixing some of these together, what will happen. Because remember, if these are ionic compounds and they're soluble, then they're floating around as the different ions. There's nothing preventing them from mixing with those other ions, which they might not be soluble with. And that's what you see happening here. So, as we were saying, if you want to predict whether you're going to get a precipitant formed, then you want to look at the ions that are there in the chemicals that you're mixing. Determine if any of the cation, anion possible combinations are soluble or insoluble, and use that table that we talked about to kind of do that prediction. So here's that example that we were talking about. So here we have magnesium hydroxide that precipitates out, but when it was magnesium nitrate, that was soluble. We had sodium hydroxide, that was soluble. Those both fully dissociate. So now we've got magnesium ions floating around, nitrate ions floating around, sodium ions floating around, hydroxide ions floating around. Got all these ions floating around in our aqueous solution. And lo and behold, magnesium and hydroxide, when those two ions get together, we get a precipitant. And once again, that goes back to our rules in that table we looked at earlier. Sodium nitrate was one of those things that we say is always soluble. We know sodium is that group 1 column, and so we know those like to be soluble, so the sodium and the nitrate still stay in solution. That doesn't precipitate out. Any questions about using that table to see if things are going to precipitate out or not. Okay, so really what you need to do is just familiarize yourself with that table, get comfortable with kind of seeing, well, what in general stays soluble when it goes into solution, what combinations could cause something to precipitate out. So there's something called metathesis. And metathesis comes from the Greek word to transpose. And so transpose or exchange, however you want to think of it. So when we say a metathesis reaction occurs, we're talking about exchanging things. And that's where we can get some of those precipitation reactions or other types of reactions. And so in this equation, this is the one we just looked at, that's where we said we had magnesium and nitrate ions floating around. And they started out where those two, when we put the magnesium nitrate into the water, magnesium nitrate was together. It went into water, it dissociated, and it dissociated fully. We know that's a strong electrolyte. And so now magnesium ions are floating around and nitrate ions are floating around. So they're free to interact with other ions if we put them in there. In this case, we put sodium hydroxide in. Sodium hydroxide, we remember from our table that that's one that's going to dissociate fully. So once again, now we have the sodium ions floating around, the hydroxide ions floating around. We've got all four of these types of ions floating around. These exchange reactions are telling us that the magnesium now, instead of hanging around the nitrate, it can go over by the hydroxide, okay? Because magnesium is positively charged, hydroxide's negatively charged. We think back to early in the semester, we said opposites attract, so there could be some attraction there. Same with the sodium and the nitrate. Opposites attract, sodium's positively charged, nitrate's negatively charged, those two can interact. When those interactions occur, takes us back to our solubility table that we talked about. And we know that magnesium and hydroxide, when those ions get near each other, we get a precipitant. So a precipitation reaction occurs, and that magnesium hydroxide will become a solid and not be in solution anymore. The way this reaction is written, we know that it becomes a solid because there's that little S in parentheses behind it. We talked about that the other day, that a lot of times when you write reactions, you'll put this information in parentheses after it. The AQ tells us that it's soluble in an aqueous solution. The S tells us it's a solid. We also talked about a G, saying that that was a gas. So here's an example where this is useful to us to remind us that that magnesium hydroxide, that precipitates out. The sodium nitrate, however, going back to that solubility table that we're going to learn, that tells us that the sodium and the nitrate, that combination, those two will stay in solution. Those will stay as a sodium ion and a nitrate ion. So we did a little bit of balancing equations, and we'll have that on the quiz, of course, on Wednesday. But we also balance these types of equations also, these exchange equations. And so there's some steps that we follow in order to do that properly. We use the chemical formulas of the reactants to determine which ions are present. We write formulas for the products, cation from one reactant, anion from the other. So we do that exchange. We do that exchange of the cation and the anion. And then we use charges to write the proper subscripts. So we need to know the charges of the cations and anions we're dealing with, so we know how many of those ions go together. Okay, is it 1 to 1? Is it 1 to 2? Is it 2 to 1? Whatever. That's based on charge, right? Then we want to look at our solubility rules. That's that table that we keep referring to. We're going to look at those rules and see if either product is insoluble. if the product's insoluble, then that would tell us that we have a precipitation that's occurred. And then we want to indicate that. We indicate that once again by that little s in parentheses next to it. And then finally, after we do all that, then we can balance the equation.
How do you tell the charge for each compound?
We'll get to that in a moment here. But the short answer is, remember when we talked about trends in the periodic table, we said that first column, those were all +1, the next one was +2, and like the halogens were -1, oxygen was -2, some of that. So some of that trending that we learned from the periodic table is our best bet for knowing that. Okay, so to write equations for these types of reactions, first we write the molecular equation, then we write something called the complete ionic equation, and then we write something else called the net ionic equation. And we'll go through what each of these mean. So the molecular equation is what you're used to seeing. This is how we've been working with things so far, where you have the reactants on the left. So in this case, lead nitrate and potassium chloride. And then you have the products on the right, lead chloride, potassium nitrate on the right. And so this tells us what happens overall from a molecular perspective. When we write a complete ionic equation, we're going to write all the strong electrolytes as if they're dissociated, because that's really what's going on in the solution, in the water solution. And so in that case, we go back here and we see these, and we know that lead nitrate's a strong electrolyte, potassium chloride's a strong electrolyte, lead chloride is a solid, and potassium nitrate is a strong electrolyte. So what we're going to do is we're going to write them out dissociated. So we have lead ions +2 charge, nitrate ions -1 charge. And if we go back looking at this equation, we see we had 2 nitrate ions for every lead ion. Okay, so that's why we have a 2 in front of the nitrate ion. Same with the potassium and the iodine. So there, when this equation was balanced, we had 2 molecules of potassium chloride. So that's why here, and we have 2 potassium ions and 2 iodine ions. Then that goes to form the lead iodide. That's a solid, so that stays together. But then the potassium and the nitrate, we have 2 on each side. Those, that's a strong electrolyte, so that dissociates. So we have 2 of those ions and 2 of the nitrate ions. So what this is doing is, this is giving us really a more accurate picture of what's going on if we looked at exactly what was in the solution. You've got all these ions floating around except for the lead iodide, which precipitates out. That leads us to the net ionic equation. So when you write your net ionic equation, you cancel out everything that is exactly the same on the left-hand side of the reaction and on the right-hand side of the reaction. So these things that you cross out, they call those spectator ions. And it just means they're not really doing anything. You've got the same amount on each side. So if we go back and look at this again, we see we have 2 NO3 minus on the left. We see we have 2 NO3 minus on the right. So there, that's a spectator ion because it's really not changing or doing anything. Same with the potassium. We have 2 of those on the left and 2 of those on the right. So if we wanted to write that net ionic, we would cross those out. And what we wind up with is lead ions plus the iodide ions form lead iodide. And this would be then that precipitation reaction in this case. So 3 different ways that we talked about writing equations in this case. Let's just go back and take a look at those again. We started with the molecular equation, and this is what we've been used to, and this is the kind of stuff we were balancing in chapter 3. So you have your 2 molecules that you're mixing together, and then you have 2 molecules that result. But what we've learned today is that really, when we have things that are strong electrolytes, they don't stay together in solution. They ionize and they're separate. So that leads us to this ionic equation, which is a more accurate representation of really what's going on inside that solution. And so there, using our solubility rules, we know whether it's a strong electrolyte and breaks apart or not, or if it stays together. And so we write that such that, in this case, the lead nitrate's separated, potassium iodide separated. Lead iodide, from solubility rules, that forms a precipitate. And then finally, the potassium and the nitrate stay separate. Because of what we call these spectator ions, which really aren't contributing to the reaction, because the reaction we're really interested in here is lead and iodine reacting to give us lead iodide. So by canceling out those ions that are the same on the reactant side as the product side, we get down to really this in this case, precipitation reaction, which shows us what goes on in terms of forming that insoluble salt. Any questions about the 3 types of reactions and how we kind of walk through those? Okay. Okay, this is what we just talked about. So there is some homework associated with this to give you some practice on writing those types of equations. That's what's up here. I will point out that on 4.29b, the correct answer is true. I think in the book it says false, but it's true. Okay, let's move on to talk a little bit about acids. So acids are substances that ionize in aqueous solution. So in other words, when you put them in water, they form, they give off, they donate a hydrogen ion. Hydrogen ion, H+, is often called, you just say a proton. So you say it donates a proton, it gives up a proton. And so here's some examples: HCl, HNO3, H2SO4, acetic acid. Those are examples of acids. In each of those cases, each of those molecules will lose a hydrogen ion, lose a proton, and it's that proton that determines how many of those protons are there, determines the acidity of the solution. So I think we're all familiar with pH, that term, and those measurements. Well, pH is minus the log of the hydrogen ion concentration. And with the pH scale, I think we probably know that the lower the value, so a pH of 1 is really very, very acidic. pH 7 is neutral, pH 14 very, very basic. So what that tells us is that the more protons that something gives off, has available, the more acidic something is. And that's how we kind of determine, is it a strong acid or weak acid? But it's that ability to donate a proton. The other thing I'll just point out on the acetic acid you see how there's CH3, COOH. This is an organic chemistry nomenclature thing, but in that case, it's the H that's all the way to the right, the one next to the oxygen. That's the one that gets donated. The 3 hydrogens next to in between the 2 C's, those hydrogens are bound to the carbon all the way on the left, and those don't go anywhere. So it's just that proton all the way on the right. So if you ever see something that's written like that, COOH, that's the proton that gets donated. With these inorganic acids, the other 3, it's always the hydrogen on the left-hand side. That's the one that gets donated. And something like sulfuric acid will lose 1 proton pretty easily, takes a little bit more to lose the second one. Okay, bases are kind of the opposite of acids. So bases will accept that proton. They can donate an OH group when dissolved in water. So bases are increasing the OH concentration, the hydroxide concentration. Acids increase the hydrogen ion concentration. That's the simplest definition of it. Bases, however, there are bases that act as a base and don't have hydroxide in them. Ammonia is an example of that. You see NH3, obviously there's no OH there, but yet it can interact with water and act as a base. And we'll have some other rules here which help us determine if something's an acid or a base. The simplest rule is if it donates OH, it's a base. If it donates H+, it's an acid. But there are some exceptions, and we'll talk about that. So strong acids, strong bases. If it's strong, that means it totally dissociates when you put it into water. So we go back to writing our chemical equations. We would have just the one-way arrow for the strong acids and bases. It says when we put it in water, totally dissociates, and we're just left with the ions. So some examples, HCl, HBr, on down the line. Sulfuric acid, that first proton comes off pretty easily, as I was saying. Strong bases, we have those 1A column things, lithium, sodium, potassium, hydroxide, a couple things in the 2A group as well. So these are our strong acids and strong bases, a partial list. There's obviously others, but these are ones that you see quite a bit. And once again, strong acid, strong base means if I put it in water, the reaction's only going one way, it's going to completely dissociate. There's no equilibrium, it just goes all the way. Okay, so let's talk about, is it a strong or weak electrolyte? First, we want to ask ourselves, is it an ionic compound or molecular compound? If it's ionic, it's going to be a strong electrolyte, assuming that it's soluble. Okay, and this goes back to that first table that we looked at where there were some exceptions on the solubility rules. But if it's an ionic compound and it's water soluble, it's going to be a strong electrolyte. If it's a molecular compound, so in other words, not an ionic compound, we need to decide, is it an acid or a base? If it starts with or ends in a proton, it's usually an acid. So there's that COOH that I was mentioning on the acetic acid. If it's not on the list of strong acids, it's probably a weak acid. Strong acid, strong electrolyte, weak acid, weak electrolyte. Same thinking with bases. If it's a strong base, going back to that table that we looked at, if it's a strong base, it's a strong electrolyte. If it's a weak base like ammonia, then it's a weak electrolyte. And once again, if it's a weak electrolyte, we're just saying that it doesn't dissociate all the way. That gets back to that, if we were to write out the chemical equation, we'd have the arrows going one way and the other arrow going back the other way. That's our indicator that something has an equilibrium to it. So once again, if it's a strong or weak electrolyte, depends on, first of all, is it ionic or molecular? If it's ionic, it's a strong electrolyte, assuming that it's soluble. If it's molecular, then we got to figure out, is it an acid or a base? And we have some help here. If it's an acid, usually there's an H on the beginning or H on the end. And if it's not on the list of strong acids, then it's a weak acid. Same idea with bases. Bases often have that hydroxide on it somewhere, the OH group. There are some exceptions to that, like ammonia. But the strong bases, we have that list there. So we want to learn some of those strong bases. And if it's a strong base, it's going to be a strong electrolyte because those strong bases dissociate the whole way. So if we take an acid and a base and react them together, that's called a neutralization reaction. And when you do that, if the base is a metal hydroxide, so if it's like sodium hydroxide, potassium hydroxide, something like that, you get water and a salt is usually what's formed. So we can write these equations similar to what we learned a little while ago, where we can write a molecular equation, then the complete ionic equation, and then finally the net ionic equation to tell us what's going on. So in this case, we're taking HCl and mixing it with sodium hydroxide. So the HCl is an acid. We know that because there's a hydrogen all the way over to the left. The sodium hydroxide is a base. We know that because there's that OH group over on the right-hand side of that molecule. And also, we know this because these were both strong acid and strong bases in that table of list of strong acids and strong bases. We do our metathesis type of reaction, and we flip, and we suddenly now have that proton from the HCl goes with the OH group on the sodium hydroxide. That gives us water. The sodium and the chloride get together, and that gives us sodium chloride. So now we use our solubility rules to decide, okay, we've got all this stuff that have changed. Is it soluble or not? HCl, we know is soluble. That's a strong acid. Sodium hydroxide, soluble, strong acid. So we write those in our in our complete ionic reaction. We have H plus Cl minus. Sodium hydroxide, we know that's a strong base that dissociates. So we have Na plus OH minus. And then that goes to form water, which we know is H2O, and then sodium chloride. Once again, going back to our solubility rules, we know that sodium and chloride will be in the ionic form. So that gets us to our complete ionic, and that tells us what it looks like in the solution. Well, then we can go and get rid of our spectator ions. And that, if we do that, we see we have Cl minus and Na plus on the right side, and on the left side, we can cross those out. And that just leaves us with H plus OH minus to form water. So that would be our net reaction in this case. And so this is why it's called a neutralization reaction. Is you took an acid, you took a base, you mixed them together, and what do we have on the right-hand side of the equation? We don't have any protons floating around. We don't have any hydroxide ions floating around. So if we had the proportions exactly correct, it would just be neutral. It would be salty water is what it would be. It would be water with some sodium chloride in it. But it wouldn't, it would be a neutral solution, it would be a pH 7 solution. And that's where the term neutralization comes from. It's like the acid and base cancel each other out, they neutralize each other. Sometimes these neutralization reactions will give off a product that is a gas. CO2 is the most common thing that you see. And here we have an example of where carbonate and bicarbonate are mixed with an acid, and we give off CO2 in each of those. So we have a salt that forms, but we also get carbon dioxide and then water. So I think it was the first or second lab when we were going to mix some of those things and we didn't get a chance to do it, one of the things we would have seen is when you do this reaction, you get a bunch of bubbles that form, and that's the CO2 being given off. This is another one, sodium sulfide plus sulfuric acid, giving you sodium sulfate and hydrogen sulfide, H2S. That's the gas that's given off. If you ever smell that rotten egg smell, that's hydrogen sulfide. You may have smelled that before, but it's pretty stinky. But that's another one of these reactions where a gas is produced. So the neutralization reactions, you may or may not realize it, but that's what these acids are based on. So something like Alka-Seltzer, some of these I'm not familiar with, but like Tums and Rolaids, those as well. So in that case, you have a neutralization reaction where the base is interacting with the acid, and that's kind of the premise of those products. The next time you take Tums or something, you can think of this. So the next type of reactions I'd like to talk about are oxidation reduction reactions. And so we're gonna learn what we mean by when we say oxidation. We're gonna learn what we mean when we say reduction. So this can get a little confusing. So we'll go over it a few times. So loss of electrons is oxidation. Gain of electrons is reduction. So the way I think of it is if something has, say, a +2 charge and then picks up 2 electrons, it goes to neutral. So it goes from +2 to nothing. Then to me, that's a reduction of that number. +2 going down to 0 is a reduction. That's the gaining of electrons is reduction. So that's how I remember reduction is a gain of electrons. Oxidation is a loss of electrons. If I'm neutral and I lose a couple of electrons, what happens to my charge? It goes to +2, for instance, if I lost 2 electrons. So oxidation is that loss of electrons. If you gain electrons, that's reduction. You can't have one without the other. If you have a reaction where something's being oxidized or reduced, you can't just have oxidation occur or just reduction occur. It's almost like it goes back to like a mass balance thing of it. If one thing is losing something, something else is picking it up and vice versa. These types of reactions, these oxidation reactions, are called redox reactions. I was thinking about this recently, and I have no idea why they call it redox reactions when you always say oxidation reduction reactions. You would think it would be ox-red reactions or something, but it's not. It's redox reactions. And so the key thing, remember, is loss of electrons, oxidation. Gain of electrons, reduction. I'll probably say that at least 50 more times to put it in class. So let's talk a little bit about some additional definition of oxidation and reduction. So oxidation, as I said, is loss of electrons. It's also occurs when you gain oxygen. That one always made sense to me. Oxidation, gained oxygen. Okay, so if something picks up oxygen, it's undergone oxidation. Also, if it loses hydrogen, that's oxidation. So there's three kind of definitions. The standard one is loss of electrons, that's oxidation. Definitely know that. But gain of oxygen, loss of hydrogen are also things that happen in an oxidation process. Reduction, we mentioned that that's the gain of electrons. So if something picks up electrons, we've had a reduction. But also, kind of the opposite of oxidation, if it loses oxygen, if it gains hydrogen, then that's reduction. So we said before that oxidation and reduction must occur together. So you can't have one without the other. And this is kind of an example of that. The things that can occur in oxidation, gain of oxygen, loss of electrons, loss of hydrogen, it's the exact opposite on whatever is undergoing the reduction. Can have a loss of oxygen, gain of electrons, gain of hydrogen. Now, it doesn't have to have all three of those things occurring to be oxidation. But it's got to have something, one of those occurring, okay? So if that wasn't confusing enough, we talk about oxidizing and reducing agents. So oxidizing agents gain electrons easily. Well, if you recall, we just said oxidation loses electrons. Oxidizing agents gain electrons. So don't get confused by that. An oxidizing agent is helping to bring about oxidation of other substances by being reduced themselves. So oxidizing agents are being reduced. Reducing agents lose electrons readily. They bring about the reduction of other substances by being oxidized themselves. So there's just a little terminology here that can be confusing. So make sure you read through it a little bit and get comfortable with those terms. Okay, oxidation numbers. We're going to talk about oxidation numbers. And the thing to recall is bullet point 2 here. This is a bookkeeping type thing. So we're not saying that the atoms actually have these charges. We're saying that we want to determine something called an oxidation number for the elements to kind of understand how these oxidation reduction reactions occur. So there's this kind of bookkeeping thing that we'll do to make sure things are balancing out. And it'll be a little easier to see when we go through some examples. Okay, when we go to assign oxidation numbers, and remember, this is just something we're using to keep track of things. Atoms in their elemental form have an oxidation number of 0. The oxidation number of a monatomic ion is the same as its charge. So, in other words, well, it's the same as its charge. Okay, nonmetals. Now remember, nonmetals were on the periodic table, those things in the upper right-hand corner over to the right of that stair step thing. So carbon, nitrogen, oxygen, things like that. Usually have negative oxidation numbers. Usually, not all the time. Oxygen, for instance, is usually -2. Hydrogen is usually +1. Fluorine and the other halogens are usually -1. The sum of the oxidation numbers in a neutral compound is 0. So what that means is that all the individual atom oxidation numbers have to cancel out if the molecule doesn't have a charge. if it has a charge, then the sum of those individual atom oxidation numbers have to equal what the charge on the molecule is. And you have to count every atom. So if it's C12, you got to count 12 carbons, okay, and have that into your calculation when you're doing these oxidation numbers. Okay, so some examples here is if we have O2, that would be 0 because oxygen's in its elemental form. We said that was one of the guides that we had. For H2O, hydrogen is usually +1, oxygen is usually -2. So does this balance out? Well, we have 2 hydrogens, so it'd be 2 times +1, and 1 oxygen, 1 times -2. So +2, -2, those cancel out, so we get to no charge on water. That looks pretty good. H2SO4, sulfuric acid. Once again, we know that hydrogen is usually 1 + 1. We have 2 of those. We know that oxygen is usually -2, and we've got 4 of those. So -2 times 4 is -8. We have 2 from the hydrogen, so that leaves 6. So it's a neutral molecule. So even if I wasn't certain what sulfur is, I know from here, because I'm pretty sure about hydrogen, and I'm pretty sure about oxygen. So you should be pretty comfortable knowing that hydrogen is usually +1, oxygen's usually +2, and then that leaves, for this to be neutral, the sulfur would have to be +6. Okay, after me telling you 20 times that oxygen is usually -2, here's one where it's -1. So how would we figure that out? Well, the way I would figure it out is hydrogen is almost always +1. So that tells me I have 2 times +1 is +2. So then it leaves me with oxygen. And if one of those is going to be different, hydrogen or oxygen, I would bet that it's going to be the oxygen. And in this case, if the oxygen is -1, then that balances out. So to be honest with you, the oxidation number stuff, you can have a feel for it, but there's a bunch of exceptions and things like that. That's where going and working some of the practice homework problems, I think, would be real beneficial. Because it just kind of gets you used to playing around with it a little bit. The last one, we have potassium acetate here. Once again, we know hydrogen is +1. Carbon is usually 0. Not always, but usually, so we're not going to worry about the carbons. Oxygen, like I said, is usually -2. We got 2 of those. So we've got -4 from the 2 oxygens. We've got +3 from the 3 hydrogens. And so then that leaves us potassium. Potassium is that 1A group. Those are almost always +1. And sure enough, that's +1, and it balances out to give us a net 0 if we add all that stuff up. Okay, so why are we worried about all this? We'll get to that in a minute here, because as we get to the actual redox reactions. So let's talk about displacement reactions. In displacement reactions, ions oxidize an element. In this case, a proton oxidizes magnesium, and the ion is displaced. Magnesium displaces the proton. So when we talk about activity series of metals in aqueous solutions, so this is kind of the reactivity of it. The elements above hydrogen. So does everyone see hydrogen there? It's between lead and copper towards the bottom of the table, about 3/4 of the way down. The elements above hydrogen, so lead, tin, nickel, cobalt, on up through lithium, will react with acids to produce hydrogen gas. Elements below copper, silver, mercury will not react. And a reactive metal is oxidized to a cation. So where this activity comes into play. This comes into play for a lot of these metals are used as catalyst, and the catalyst is something that just makes a chemical reaction go faster or quicker or something like that. And that's where some of this metal reactivity stuff comes into play. But for our purposes, we just kind of want to remember that hydrogen is kind of the cutoff on this table. Things that are above it react, things that are below don't react. This is kind of what we just talked about with these metal acid displacement reactions. Higher on that series, the higher they are in that series, the more reactive they are. And then here's some homework for that stuff that I would recommend, especially to get a feel for those oxidation states. Okay, I want to save molarity for Wednesday. And so I think we'll end it here for today. Does anyone have any questions? Okay, just a reminder, on Wednesday, what we're going to do is we'll go over the molarity and finish the chapter off, and then we'll have a quiz on chapter 3. So the quiz is just on the chapter 3 stuff. All right, thank you.
We come in on Wednesday?
Well, it's up to you. If you want to be here for the lecture, you can come in. But to take the quiz, you can take it in here, or I will be here for, the lecture. So if you want to be here to take the quiz, I'll be here. That's fine. If you want to dial in for the lecture part and take the quiz wherever, that's up to you.